We're looking at the second page of the worksheet 1 for AP Exam Review 1. So this second page is just miscellaneous topics, limit definition of derivative, as well as related rates involving rate of change of angle measure, as well as some limit problems dealing with L'Hopital's rule. So let's look at, let's recall some, review some information here, some topics. Limit definition of a derivative. This is notation for expressing derivative of a function or evaluating the derivative at a point. So a derivative function, we learned a while back with the limit definition of a derivative. Limit as h approaches 0 of f of x plus h minus f of x over h. It's just a fancy way of representing the derivative at a point. So we know this notation represents f prime of x. If we want to evaluate the derivative at a point, we can replace the x with a particular c value, and then this c can replace all the x's, and that will allow us to evaluate the derivative at a point where c is a value. And so limit as h equals 0 of fc plus h minus fc over h represents the slope at a particular point. There's also the derivative alternate limit definition, which is the limit as x approaches c of f of x minus f of c over x minus c. So this also produces the derivative at a point. But let's look at a couple of examples here. So the first one here, it says find the limit as h approaches 0 of x plus h quantity fourth minus x to the fourth over h. Now this may look like a problem that we want to expand all the way and then algebraically try to evaluate the limit, but this is actually going to be more of a conceptual problem to see if students can match this with a particular with conceptual understanding of the limit definition of a derivative. So if we were to match this up, we see that this matches up nicely with its derivative function. We see the x plus h represents the f of x plus h. We see the f of x is represented by x to the fourth. So this is essentially saying this represents the derivative of a particular function. This is representing f prime of x. So if we know that f of x is x to the fourth, is x to the fourth, right? Then if we just go to what we know, how do we find the derivative of x to the fourth? Well, we can just go through a power rule. So x to the fourth becomes 4x cubed. So then this is now represented by 4x cubed. So the understanding here is if we can pull the appropriate function from this notation, then we know that this is simply asking for the derivative of that particular function. So if we can look at this notation and pull out the necessary information, which is that the function that this is referring to is x to the fourth, and this notation is asking for the derivative of x to the fourth, then there's no longer a need to look at this notation. We can just go directly from x to the fourth, and power rule will give us 4x cubed. All right, let's look at the second one here. This is another conceptual problem that deals with limit definition of a derivative. Notice that tangent of x plus h represents this portion of the limit definition. F of x is therefore tangent of x, and then everything looks like it's in the right place. So really this is asking for the derivative for a particular function. Okay, and that particular function is tangent of x. So if we think about what the derivative for tangent of x is, we know from our trig rule for derivatives that the derivative for tangent of x becomes secant squared of x. So therefore answer choice C. Okay. All right, let's take it one step further here. What is the limit as h approaches 0 for this expression? Now notice that there are no more x's in this notation. All the x's have now been replaced with the c value. Okay, and this c value is 3 pi over 2. So this is asking for information that is one step beyond similar, but it's going one step beyond what it's asking for here. This is not simply asking for the derivative of a function. This is asking for the derivative of a function at a point. Okay, so we have an additional step that we need to do in addition to finding the derivative. We need to evaluate that derivative at a particular point, and that particular point is 3 pi over 2. So if we look at this, we should be able to tell that if this is representing f of c, then we know that f of x must be cosine of cosine of x, right? So if cosine of x is the function that we're pulling from this notation, and this is asking to find the derivative at a point. This is a two-step process. We first identified our function. Next, we need to find the derivative. So the derivative for cosine of x is negative sine of x. And then one step further, it's asking for the derivative at a point. So it's asking for what's f prime of x. We know that f prime of 3 pi over 2. We know that f prime of x is negative sine of x. So if we replace the x with 3 pi over 2, sine of 3 pi over 2, which is negative 1, negative 1 times this negative 1 outside will give us positive 1. Next question here is similar notation. Natural log of x plus 3 minus natural log of 5 over x minus 2. So we can see that this is actually going to match better with this notation, this alternative or this alternate limit definition. Okay, so if we can pull what the function is, right? Function is simply just going to be this natural log of x plus 3. Okay, and it's asking for us to find the derivative at the c value, and the c value we can notice is going to be 2. So the information that we're pulling is going to be a little bit slightly different location, but it's the same idea. We identified the original function. We know we're going to find the derivative, and then once we find the derivative, we're going to evaluate that derivative at a particular c value. So our function that we're working with is natural log of x plus 3. We're going to find the derivative. So the derivative for ln of u is u prime over u. So our u prime is just going to be 1 plus 0, which is just 1. All over u value, or u value is everything inside the parentheses, so 1 over x plus 3. That's our f prime. Now we want to evaluate f prime at 2, so replace 2 into the x's for my f prime. So 1 over 2 plus 3 is 1/5. Okay, another topic here is limit problem using L'Hopital's rule. So if we look at this problem here, the first thing we do is we plug in our 0. And in this case, we get 0 over 0. And if we get 0 over 0, usually we look to see if we can factor. So this problem, we can actually factor this out. Factor out the x squared, numerator and denominator, x squared cancels out. Reevaluate zeros into the remaining expression. We get negative 3 over negative 2, which is 3/2. Okay. Another way that we can approach this is we can go through L'Hopital's. As soon as we get 0 over 0 or infinity over infinity, then the condition is right for us to go through L'Hopital. So that's another option that we can take. L'Hopital's, we're going to find the derivative of the numerator, and then separately we find the derivative of the denominator. So 20x the derivative for the numerator, 5x to the 4th becomes 20x cubed. 3x squared becomes 6x. Denominator, we get 16x cubed plus 3x squared minus 4x. Now we can reevaluate the limit or the expression, and we still get 0 over 0. If we get 0 over 0 again, then we can continue with the derivative procedure. But one thing you have to be sure of is each time you find the derivative, if you're doing L'Hopital's rule, you can't just jump directly to the next derivative without first checking to see if you get this particular indeterminate form of 0 over 0 or infinity over infinity. So we tested it. We do get 0 over 0, so we're going to reevaluate, we're going to go through L'Hopital's again. So go through derivative power rule. We get 20x cubed becomes 60x squared. 6x becomes 6. Denominator is 48x squared plus 6x minus 4. We reevaluate the limit. We get 6 over 4, which is 3/2. 3/2 is a real number, so that's our answer. All right, in the triangle shown, if theta increases at a constant rate of 3 radians per minute, at what rate is x increasing in units per minute when x equals 3 units? So we have our triangle here. We have theta, x, and 5. We're trying to find the rate of change of x given that theta is increasing at a constant rate of 3 radians per minute. So we know theta increasing at a constant rate, that must be referring to d theta over dt. So d theta over dt is 3 radians per minute at the moment when x is equal to 3. And we're asking to find the rate of increase of x, which is looking for dx dt. So we need to first start off with an equation that relates theta and x. So we're going to use a trig ratio here. So the trig ratio that will relate theta, x, and 5 will be sine, because we know sine of theta is opposite over hypotenuse. So sine of theta is equal to x over 5. From here, we can find the derivative with respect to time to help us arrive at the variables that we're looking for. So sine of theta becomes cosine of theta times d theta dt. X over 5 is the same thing as 1/5 x. And the derivative for 1/5 x is just going to be 1/5 times dx dt. All right. So let's see what we know here. We know that this is 5. This hypotenuse is 5. We know that at this particular moment, x is equal to 3. So if x is equal to 3, which is the vertical portion, the vertical leg of this triangle, we know the horizontal leg, if this is a right triangle, must follow a Pythagorean triangle here. So a squared plus b squared equals c squared, and we know it's a 3, 4, 5 triangle. So we know the other leg is going to be 4. So we know at this moment in time, cosine of theta is equal to 4 over 5. So that will allow us to replace a value for cosine of theta, since we don't have a calculator to figure out what cosine of theta is at this moment in time. So cosine of theta gets replaced with 4/5. D theta dt gets replaced with what was given in the problem, which is 3 radians per minute, equal to 1/5, that's coefficient, and then dx dt is the missing variable that we're looking for. So dx dt, we can just multiply the 5 over, multiply by the reciprocal. The 5's cancel out. 4 times 3 is 12, so dx over dt is 12 units per minute.